Okay, so today we're going to start our last topic of this class. It's about sampling from a distribution. So what is different from our previous lecture is that these sampling methods are not standalone methods. They are a technical step for doing statistical modeling. So what we mean by that is when you build a model such as, for example, the hidden Markov model is a model, or the Gaussian mixture model is another model. So a probabilistic model is something you can write down its probability density function of data given a model, which can be translated into the likelihood function of the model parameters. That is how we do modeling. But once you obtain the model, there are two routes to go. So one is to do frequentist statistics. So what we mean by that is that given a model, you need to come up with an estimator for each parameter. And the estimator is a function of your data. For example, you can come up with the sample mean as the estimator of the population mean. You can come up with the sample variance as the estimator of population variance. You can come up with the sample Pearson correlation as the estimator of the population Pearson correlation, etc. So you have such examples in the frequentist sense. In the Bayesian sense, if you recall, we talked about for each parameter, we assume itself is random. So the parameter follows a prior distribution. And then combining the prior with our data distribution, which is the likelihood, we get a posterior of the parameter. So in other words, in the posterior, we have, that's the motivation here. In Bayesian statistic, we have the posterior, which we often write as theta given x. So this distribution is what we call the posterior. And given this posterior, what do we do, right? If you're a Bayesian person. For a pure Bayesian person, you would talk about how you infer the parameter given your data with the posterior. For example, if the posterior has a density function like this, okay, so let's say that here it's probably, I would say 0, and you will say, oh yeah, it's symmetrical 0. If this is my posterior, then what would you say about your parameter given the posterior? You will probably say, yeah, I would just guess the parameter is 0. Okay, you could guess it based on the mode of the posterior, or it could be the mean of the posterior. So you can have multiple ways to summarize this posterior distribution into one number. And that number would become your estimator of theta. So in other words, using Bayesian as a framework, you can come up with an estimator theta hat. So for example, you could define theta hat as we call as the maximum A posterior. This is the map, short as map. This is just the mode of this distribution theta given x. So that's one way to define an estimator in the Bayesian framework. Another way is to define that as the Bayes. We call the Bayes estimator. That's the expectation of the posterior distribution. So given the posterior distribution, you can define another estimator. But ultimately, to extract or to condense, I should say, to condense the posterior distribution into an estimator, it usually involves how to compute the expectation or how to compute the mode, right? So these are two mathematical questions you need to address given the posterior. And usually, the posterior is only known as it's only known without the normalization constant. So what we mean by that is using the Bayes theorem, what we get is the posterior density is proportional to the prior times the likelihood. Okay, and the likelihood itself is actually the density of data given theta. That's what you have. And usually you can easily write down these two terms and their product by ignoring the constants that has nothing to do with theta. So for example, I may, under the case when the data distribution is Gaussian and the prior is Gaussian, I may have the posterior known as something like Gaussian as well. So I can write it proportional to the exponential function of something, I would say 2 sigma 0 square. I'm just making up the name, the notation, and to the power, in the numerator is theta minus theta 0 square, something like that. So you know that here it's an unnormalized posterior because clearly this is unnormalized because the right-hand side, if I do the integration, is not equal to 1, okay? Because, let me just write this again. If I do this, and know that this is the density of theta, so I do d theta, and this is not equal to 1, which means that it's not a properly normalized probability density. So with this, if you don't know how to do the normalization, or if you don't know how to do the integration, it becomes very difficult to calculate the expectation of this posterior because expectation involves this integration. So what I mean is that, so the expectation of theta given x, like this, if I say it's theta times the density, posterior density d theta, it can be difficult to calculate. So when this happens, what's your alternative? If you cannot simply do integration, then we have this important technique called the Monte Carlo method. So the Monte Carlo method, in short, is to use a sample from the distribution and take the sample average as an approximation to the expectation of the distribution. So what we mean is that, let's say we just do sampling and we call our sample theta 1 to theta n, a large n. We sample them independently from the same posterior distribution. If we can do that, then we use the average of our samples, our sample average, to approximate the posterior mean. So in other words, as long as you can do sampling, you could approximate the expectation without using integration. So it's say you use computation to save the effort of mathematics, in other words. Then the question is, how do we sample from a distribution? So it depends on how much we know about the distribution. So in the simplest case, we know the CDF of the distribution, and we call it F. So the cumulative distribution function. So what we mean by that is here, let's say, if we have a random variable x that follows the CDF, then the definition of F at any value that this random variable x takes, I call that lowercase x, is defined as the probability that this random variable takes value smaller or less than this x. So please know that here we're just talking about univariate random variable and its CDFs for simplicity. So x is just one dimensional. Okay, So if we know this, and we know that the f is just monotone increasing. It goes from 0 to 1. So that's the definition of probability, okay? So then what we can do is that we can define the inverse of the f. Okay, the inverse of f, so please know that the f maps from the domain of the random variable, is a function that maps from the domain of the random variable to 0, 1. Okay, then its inverse is defined as the map that goes from this interval to the domain, goes back to the domain. That's how we define the inverse. And then what is the definition of the inverse? So actually for continuous f, it's very obvious. It has a unique inverse. So for example, for continuous f, what I mean is that, so let's say these are the possible values of my random variable, and this is the CDF, so it's confined to 0 to 1. So by continuous, I mean that your f looks like this. So there are no breakpoints in the middle. Then the f inverse can be directly identified or defined as whenever you have a value here, you go here, find the curve, and go down to find the corresponding value. That will be the f inverse. So for any value, let's say y in here between 0 and 1, this f inverse y will be here. This is the most straightforward way. But whenever you have a breakpoint, then it becomes a little more complicated. Okay, so if you have a breakpoint, what does it mean? So this is related to how we define the CDF. So note that it's defined as less or equal than. So if you have a gap in the middle, let's say here, and it suddenly jumps up. So what this means is that your distribution of the random variable is not continuous. You do have a point mass right at this, I call it x0. So it means that this x0 value itself has a probability that is greater than 0. And that probability is just by the gap. So if the gap is just a P0, then what this means is that the probability that my random variable takes value lowercase x0 is equal to P0. And this is not continuous because we know for continuous distribution, the probability that my random variable takes any single value is equal to 0. That's how we mean continuous distribution. So when this happens, you see, we have some issue with defining what's the inverse. So for example, if your y falls in the middle, right? If this is your y, if it's just falls in the gap, then for all these y, its inverse is going to be defined as x0. So therefore, for that f inverse, you need to account for that fact. So to be exact, how we define the f inverse, it is defined as, so let me say f inverse y. It is defined based on the values of the x such that fx, okay, this fx is greater or equal than the y. So you need to cover it, and also what you need is you want to take the minimum of the x. So in the case that we have continuous, then we just use the infimum. So for all the x that satisfy its CDF is greater or equal than y, we take the smallest of those and define that as the inverse. I think I made a mistake, sorry. Let me see if I'm right. Fx0. Yeah, exactly. Yeah, so I think I'm right. So this is how we define the CDF and the inverse. Okay, so do we have any questions? me see. Yeah, I think I do have a mistake. I think it should be x0. Yeah, I think it should be circle here and it should be solid above. Yeah, that's right. So because here it means that we didn't reach x0 yet, so that we didn't add the probability of x0 into account. Once we reach the x0, then we add the probability into account. Yeah, that's right. Okay, so then given the F inverse, this definition, now we have a way to do sampling under F. So what we utilize is just what we call random number generator in our computer. So the random number generator will allow us to sample IID from uniform 0 to 1. So based on random number generator, what you can do is that you can always sample U1 to UN IID from uniform in the interval 0 to 1. That's what you can do. And then you just need to apply F inverse to your sample and obtain F inverse U1 to F inverse UN. And these numbers will now follow IID from F. This is just by the definition of CDF. We can achieve that. The reason is, okay, so if I denote my XI by F inverse UI. So if I do this definition, then the reason is that for the CDF of XI, if I do what is the probability of XI less or equal than a value X, then you see I can just plug in what I define for my XI, F inverse UI less or equal than X. Okay, and then by the definition of F inverse UI, what I can have is that this is essentially UI less or equal than Fx. Okay, I can show it's equal to that. Then because UI itself, or sorry, my bad, it's just, I should write probability, not F. So the probability of this is equal to probability of this and equal to probability of this. And then because UI itself is uniform 0 to 1. So then this probability is just Fx. This is just because UI is uniform 0 to 1. So essentially we show that Xi follow the CDF. That concludes the proof. So it's just one line proof. So this is the simplest way of generating data from any distribution for which you know the CDF. And this is how our computer implements sampling from a normal distribution, from a Poisson distribution, from a gamma distribution, etc. So you have to know the CDF. Okay, does that make sense to everyone? So once you know the CDF, you can compute the inverse, then you're done. Okay, and in the notes, you can see that we have shown you a case which is a very straightforward application of the Monte Carlo method for calculating the area, the difference in the area between a square and the circle. So if you know how to do it in a mathematical way, you could compute it exactly. And if you don't, you could use Monte Carlo to do random sampling from the square and from the circle. And then you can just count what's the proportion of data points that fall out of the circle. Then that will give you an approximation for the area. So that's just a direct application of Monte Carlo method. Okay, this is straightforward, but now we're getting more complicated. So what if you don't know the CDF? You just know the density up to a constant. Okay, so we don't know F. And we just know the PDF, probability density function F up to a constant. So in other words, the F is not really a density that can integrate to 1. It's just proportional to the density with the constant omitted. So then, what do we do? So here is what we call the rejection sampling. So our idea is to find a density G, or a PDF. I can also say the PDF G, from which we can easily sample, like a Gaussian density, exponential density, those common distributions densities, from which we can easily sample. And there's a requirement, that is, and that there exists a constant, is a constant, positive constant, m greater than 0, such that when we do m times g, it's always dominating our f. So for any value in the domain of our random variable, so this density we arbitrarily find can always cover our target density with a constant. If we multiply by a constant, we can satisfy that. And this means that we have a cover or an envelope. Okay, so then what we do is that we are going to draw a sample from G. Okay, so what we do is that we randomly sample point xi from G, from this density we find. And what we do is that we compute a ratio. Compute a ratio which is defined as Ri. So if the ratio is defined as, we use the sample value, the value we sample, we put it into the target density fxi, and we divide by the envelope m times gxi. So clearly by the definition here, this is between 0 and 1, right? This must be positive, non-negative, and no greater than 1. And so then what we do is that we are going to draw a Bernoulli random variable from a Bernoulli distribution with this ratio as the success probability. So we draw, or we can say we sample, I call it Zi, from a Bernoulli distribution with success probability equal to Ri. Then if Zi equals 1, we keep xi in our sample. Otherwise, if Zi is 0, we just discard xi. That's why we call this rejection sampling. So essentially, we sample from an easy distribution, and we just don't keep everything we sampled. We keep the sample, we keep every value we sample with a certain probability. And that probability is defined as the ratio of the target density and the envelope density. Okay, so why does it work? I can show you a graph to help you understand that. So let's say that our target density, okay, this is the density. Let's say that our target density has a weird form like this, and this is my fx. Okay, if I can find a nice envelope like a Gaussian distribution, like this. So let's say this is my m times gx. So it well covers the target at every value. Then what it means for the rejection sampling is that if I happen to draw a value right here, then you see this will be the ratio. The ratio will be equal to this short segment divided by the long segment. And here the ratio is close to 1, which means that I have a high probability of accepting this value. But if I happen to draw a value right here, x2, then at this x2, the short segment is much shorter than the long segment, so the ratio is close to 0 instead of 1. Then I have a low probability of accepting the value here. So in other words, when you do rejection sampling, although you are sampled from the envelope density, but because your rejection depends on how much the two densities agree with each other. So then you can modify the sample by discarding the values where the two distributions differ quite a lot and keeping the values where the two distributions agree quite well. So that's why after this modification, your sample will come from this target density. That's the idea of the rejection sampling. Okay, does that make sense to you? Okay, so then formally, why does it work, right? Why does this procedure work? So essentially what we do is that we only keep the sample whose ZI is 1. So to show that it actually worked, what we need is that we need to show the density of xi conditional on zi equals 1. For these values, they come from F. That's the thing we want to show. Okay, so how do we do it? So in order to derive the density of this, the conditional density of this, what we need is, so I'm just going to write lowercase xi given zi equals 1. We are going to use Bayes' theorem again. This is equal to the joint density of xi and zi equals 1. So please note that this is a mix of a continuous random variable and the discrete random variable. For zi is discrete, but xi is continuous, divided by the probability that zi equals 1. So we need those. And then what is the numerator? So you see, the numerator is essentially, we can write it as the probability of zi equals 1 given xi. The reason I write it that way is because when we do sampling, we first draw xi and then we draw zi. So this is aligned with the sequence of our sampling times the probability density of xi. And note that xi is sampled from G density. So that density is gxi. That's the numerator. And for the denominator, I'm going to write it out also. So for the denominator, moving here, we know that it's equal to the sum of two joint probabilities. That is, it's not that. It's actually equal to the integration, I should say, the integration of xi. So we need to integrate out xi in this joint density, so we keep zi equals 1. So it's the integration of this joint density of xi and zi equals 1 dxi. So we're going to do this. And what is that? You see, based on the same argument, it's equal to the probability zi equals 1 given xi and the density of xi, that's gxi dxi. And we haven't talked about what this conditional probability of zi equals 1 given xi is. That's the Bernoulli Ri. And Ri itself is fxi divided by m times gxi. So that will give me fxi n times gxi, you see, and gxi dxi. And we have cancellation here and here. Okay, and we're left with the fxi. So please note that the fxi is only known to some normalization constant. So it's not a real density. Don't forget that. So then we would have it equal to some constant. So I'll just write it as integration fxi dxi divided by m. That's pxi. Okay? Pzi, probably z equals to 1. Then putting this back into the ratio, what I would have is for the conditional density of xi given zi equals 1, I would have, so here in the numerator, I'm going to use the ratio for the Bernoulli as well. So that's, see, fxi divided by m times gxi times gxi. In the denominator, that's here, I have the integral of fxi dxi over m. Okay, so you see, I have cancellation in the numerator, and the 1 over m got canceled here. So what I have is just fxi divided by its normalization constant, you see. That's a valid density. So this is the normalized f, and that's what we want. So essentially, we have proved that the rejection sampling can indeed make our retained sample to become from the target density, which should be the normalized f. And we can achieve this by not normalizing f. You see, if we want to go use the first route, we need to obtain the CDF. And to obtain the CDF, you need to find a way to normalize the PDF and then do the integration of PDF to obtain CDF. That's the route you need to go. But because here the integration itself is difficult, we don't want to do that. So we just get around this problem by sampling from an easy distribution G, by just making sure that we can find the constant, no matter how large the constant is, we can have m times G cover the unnormalized f. And then we just sample from G and use the rejection sampling as this to just modify our sample, and we're done. But you can see that in order to make the rejection sampling efficient, you want to find a nice cover. That means for the most part of your domain, the domain of the random variable x, the values that x can take, you want to have the two density functions close to each other. So it's barely a cover, and that will be the ideal case. So that will give you large ratios for the values you draw, and there will be large probability for you to keep the drawn value, and that will give you very efficient sampling. Because otherwise, if you discard too many of the values you sampled, you will be slow. For example, if the rejection rate is 90%, to get 100 values in your sample, you need to do sampling for 1,000 times, and that's not computationally efficient. So we are going to give you an idea about this envelope thing. So that's the example in our lecture. So how to choose a good envelope. So here, let's say that our target density is just a truncated normal density, okay? So let's say our fx is proportional to the density of normal distribution. So there's a typo in the notes. So that in the notes, they use the uppercase 5, but that's usually used to denote the CDF instead of the PDF. So here we should use the lowercase 5 for the CDF times the indicator that x is greater than c. So where phi is the PDF of standard normal. So what we mean here is that if you have the normal distribution, like normal 0, 1, like this, okay, so if you set C equal to here, so what you want to keep is only this part of the density. So in other words, all your sample will be greater than C. You will not have value coming from this part of the region. And then how are you going to do the sampling to draw from that truncated normal? So of course, the first obvious case, even if you don't know the rejection sampling, I think everyone will have this intuition. That is, why don't I just draw a sample from the standard normal, and I only keep the sample for those values who are larger than C. I keep those and I discard the rest, right? That's the most intuitive way. And this is translated to what? You are essentially using the whole normal density as the envelope, right? So that's our method 1. And that's the naive way. That is, you just sample from standard normal, okay? And then you keep the sampled values greater than C. Okay, so translating this to our rejection sampling, you are going to have, in other words, translating this to our rejection sampling, if your sampled xi is greater than C, then in this part, the envelope and the target agree with each other. So the ratio of acceptance is equal to 1. So you keep the sample for sure. If it's less or equal than C, on the left-hand side, you don't keep the sample at all. So the acceptance ratio for the Bernoulli is equal to 0. So this is the rejection sampling interpretation of this approach. But clearly, when the C is super big, it doesn't need to be super big, but we know the normal density is quite concentrated around 0. So when C is like close to 2, then this tail probability is only 2.5%. Okay, for 2, this is only 2.5%. So you are going to discard 97% of your sample and only keep 2.5%. That's not efficient at all. Okay, so that's the issue with this approach, inefficient. So when C equals 2, you're only going to keep 2.5% of your sample. So it will take a long time for you to reach a reasonably large sample size. So then let's take a look at the shape of the density. And we know that Gaussian tail or normal tail is decreasing very fast. So a better idea is to use another density to cover it. And we can actually use a shifted exponential density to cover it. So if you recall, use a shifted exponential, exponential lambda density. So we know that an exponential density has the form, let's say this is x, so that density has the form lambda to the power negative lambda x. Okay, so an exponential is defined for positive real values. So for it's 0, when it's 0, we get lambda. I should write it here. We get lambda here, and it decreases as our x goes large. So that's the exponential density. So what we want to cover this is to shift this 0 to C. Okay, so hopefully we can shift it to C, and then this part must be close to this part, and it decreases slower than the Gaussian tail. then this can cover it totally. So that's our goal. So we want to shift this density so that this 0 becomes C. That's our first shift. And the second question is to find the lambda, a proper lambda, so that this exponential density with multiplication of a constant can totally cover this Gaussian tail. That's what we want. So with the shift, the g, let me say the g of x with the shift can just be defined as lambda times exponential to the power negative lambda times x minus c. So this means that I change the domain, I shift domain from 0 to infinity to c to infinity. So here the x must be greater or equal than c. That's the new domain for this density. And then we want to find a constant m. Remember that constant? Such that we can have n times gx be greater or equal than fx. This is our fx for all x greater or equal than c. Okay, that's our goal. And also, don't forget that g involves lambda. So we need to find that lambda value also. Okay, so to be able to do that, we need to know what's the shape of fx and what's the shape of gx. So gx is right here, and for fx, so now let's move back to here. So this phi is the PDF of standard normal. So we know that the phi of x has this form, 1/√2 pi exponential to the power x squared over 2. That's the probability density function of standard normal. And we're going to use that here. So essentially, we can show that with this relationship, we would have m greater or equal than fx divided by gx, okay? And I will put the terms here. So that's 1/√2 pi exponential to the power x squared over 2. And in the denominator is lambda times exponential negative lambda x minus c. So you see, after some term merging, I would have 1/λ√2 pi exponential to the power x squared over 2 minus lambda x. I think there's a typo in the notes. It should be plus lambda c. Yeah. Oh, sorry, lambda x. Wait, it should be minus lambda x. I do that, it should be plus. Okay, and it should be minus. Yeah, that would be correct. And let's see. Let me see. Because this is plus and minus. Right, this is correct. Minus lambda x plus lambda c. Okay, so then with this expression, what we need is to find the m so that for any x, okay, so this is for all x greater than c, the m must be greater than these. So that means we need to find the maximum value of this right-hand side for x greater than c. And that maximum needs to be set as my m. Okay, so therefore, m must be set to the max of x greater or equal than c of this right-hand side. Put it down here. And essentially, it becomes an optimization problem. We want to see in this range, x greater or equal than c, what is the x value that maximizes this term? You see, maximizing this term is equivalent to minimizing the square term without a negative sign in the exponent. And we can solve that as a squared optimization problem. So I'll skip the step, but we can show that this maximum is actually 1/λ times √2 pi exponential to the power lambda squared over 2 minus lambda C. That's it. That will be the maximum. Okay, so you see, we find the constant. And that means for any exponential density lambda, we can always find an m, set m to that, and we can achieve the envelope. But out of all the possible exponential density, we still want to find the one that gives us the highest acceptance ratio. So how do we do that? We just want to find the lambda here so that the m is smallest. Okay, so now m depends on lambda. But out of all the possible lambda and their corresponding m, we want to find one particular lambda value for our exponential density so that m is smallest. So for m being smallest, we mean that we have the closest, or we have the envelope closest to the target density. That's what we want. Okay, so then the problem is to find a minimizer of this. Okay, which lambda minimizes this? So I can call this m lambda. So just to make it clearer for you. Then finally, find lambda to minimize m lambda. Okay, and ultimately, we can see that, I'm going to skip the detail, but the lambda will be C, will be equal to C. So essentially, finally, we find the envelope as the shifted exponential as equal to C times exponential to the power negative lambda or negative C times x minus C for all the x greater or equal than C. So we're going to use this envelope, and the m, the corresponding m, is equal to, so we just put this lambda equals C back here. The corresponding m is 1 over C times root 2 pi exponential to the power negative C squared over 2. So with this constant and this envelope, so we will have m times gx greater or equal than our target fx for all x greater or equal than C. And we're done. So ultimately, we're going to draw a sample from this shifted exponential. How can you do the shift in programming? What you can do is that, so in practice, I can tell you what we'll do, is that you can do sampling xi from exponential function, exponential distribution with rate C, okay? And this is the unshifted version. And you are going to change xi by adding C. Okay, so the first step is to sampling, second step is to do xi plus C. You add a C to the value you sample. And then the third step is to compute the ratio. So you are going to compute the ratio Ri as fxi. So this is the unshifted a shifted version. So fxi plus C divided by n times the gxi, the unshifted version. And the g is just exponential density. Okay, and then, so this is the density of exponential C. Let me see. Okay, and then with this ratio, you are going to draw Zi from Bernoulli Ri. And then based on Zi being 1 or 0, you do rejection or acceptance. So Zi equals 1, you keep xi, and equals 0, you discard. So that will be your final decision. So this is the implementation of this rejection sampling. And in the notes, you can see that the larger the C, the better the advantage our exponential, this approach has compared to the naive approach, for which you just sample from the normal and then you just use C to make this decision. So that will give you very small acceptance when C is very large, but the advantage of this approach is getting bigger and bigger as C gets larger. Okay, so that's the rejection sampling. So the challenge here is translated from how to find the CDF of your density F. That can be quite challenging to the problem of finding a proper envelope density. And the envelope density must be of a distribution from which you can easily do sampling. Okay, that's the rejection sampling. Do you have any questions? Okay, the third thing I want to say is that in some cases, if you only care about the Monte Carlo, okay? So if your goal is only about finding a way to draw sample from a distribution and to approximate expectation of some difficult distribution, you may use importance sampling instead of rejection sampling. So that means you don't need to discard your sample. You just want to re-weight your sample in some way. So this can be more efficient. So of course, still you don't know F, right? Otherwise, you will use approach 1. You just know the PDF F up to a constant, same setting. And you're only interested in some integration, some expectation under the density F for some transformed random variable, I call that hx, where x follows the density of your interest, the target density F. So that if that's your only target, then you could do importance sampling instead of rejection sampling. Okay, so what is that? Again, you are going to draw your sample from the distribution that is easy to sample from. And here, the distribution it doesn't need to be a cover. You just need to have a distribution that's easy to sample from. So we call that a trial distribution or trial density G. So from which you can easily sample. Okay, that's the thing we need. And then the first step is that we just draw x1 to xn as IID from G. Okay, and the second step is that we calculate importance weights for each point. And the importance weight is calculated as Wi equals to the ratio of the two densities. So that is pi, oh, I should say fxi divided by gxi. Okay, so for every point, we have a weight associated with it. And then we are going to just do this. The third thing is to compute or approximate the expectation under f of hx by a weighted sum. So that will be equal to summation I from 1 to n hxi of your sample value times the weight wi divided by the sum of the weights wi. Okay, So what this says is that for the weights, so for the values for which the target density is bigger than the trial density, you give them more weights. And for the values for which the trial density is larger than target density, you give those values smaller weights. And that makes sense because essentially when the target density is greater than the trial density, it means that you should have observed this value more frequently under the target density than you have achieved using the trial density. So those values deserve to receive greater weights. Well, on the other hand, if the value has greater trial density than target density, it means that you should have observed less frequently under target density than you have observed under the trial density. So you want to give them less weight. That's the intuition behind it. Okay, does that make sense to you? Okay, and then we can easily show that essentially this importance sampling will give you the approximation to this way. So the advantage here is that you don't need to throw away any of your samples as you do under rejection sampling. You just reweight them. Okay, so that's what I want to say for importance sampling. And this is very widely used in a lot of bioinformatics software. If you want to come up with an estimator from your posterior, and if you cannot easily draw from the posterior, but you can sample from another density, you can just use this weight to adjust the expectation so that you can compute the expectation from the posterior. But what I want to say is that all the three approaches, what we talked so far, the F inverse transform, rejection sampling, importance sampling. So these forms can only be easily used for univariate density. That is, the F distribution density is for a scalar value random variable. If you have a multi-value or multivariate density, they do not work well. It's not easy to use them for multivariate density. Okay, so they all work for univariate function f. Okay, so that's their limitation. But that's usually not the case for our model because a lot of times our model parameter is multidimensional. Just like in the linear model, how many predictors you have, then how many parameters you want to estimate about. So it's not a univariate problem, it's multivariate. And if you want to estimate multiple parameters together, then the posterior would be multidimensional. So the reality is that a multivariate density. So for example, let's say that in the linear model, so we can call that Bayesian linear model. Our beta is p-dimensional. P is the number of predictors plus the intercept. So when that happens, then beta, given our data, would follow a multivariate normal density and p-dimensional normal density. So the mean is p-dimensional and the covariance matrix is p by p. So that's the multivariate case. And this is something easy because we know, okay, the posterior is multivariate normal. We can easily sample from multivariate normal, or we can easily get the multivariate normal mean. That's the posterior mean, and we're going to use that as our Bayes estimator. So we have seen a similar case, but not under the normal, but under the, you remember the inverse chi-square distribution we have used for the variance parameter when we talk about the t-test. We said that when the sample size is too small, the variance cannot be stably estimated, so we use the Bayesian estimate by putting an inverse chi-square prior, and the posterior of the variance parameter is inverse chi-square also. So we use that approach. So for conjugate prior, usually when the conjugate prior is specified to be a nice distribution, by conjugacy, we know the posterior is in the same family as the prior. So the posterior is also a nice distribution. So we don't have this issue at all. But if you want to be more flexible, if you are like a real Bayesian person, you want to make the prior a lot more complicated, not just conjugate. So in that case, your posterior can turn out to be super complicated. And that's something you can see a lot in a lot of bioinformatics papers, method papers. If they say, okay, I use Bayesian modeling, sometimes their posterior can be super complicated, and it's multivariate also. So then how can you sample from that complicated posterior? That's the case. And motivated by this challenging question, we have what we call MCMC. So it's called Markov Chain Monte Carlo. So the two MCs mean different things. The second one is what we have learned, the Monte Carlo method. That is, you want to draw sample from a distribution. Use the sample mean to approximate the expectation of the distribution. That's the same MC, Monte Carlo. Markov chain means that we are not doing this IID sampling as we do before. Recall that IID sampling is based on random number generator. Whenever you generate a random number, it's independent of the previous number or the next number. So you naturally have IID from a uniform 0 to 1 with a random number generator. But that Markov chain means that when you draw a sample, you just draw one value conditional on the previous, and given the current value, you draw the next. So that's just the nature of a Markov chain. You know, Markov chain is different from IID in that two adjacent variables are dependent. So to help us understand that, let's do a quick review of what we call the Markov chain. So a Markov chain is often written as x1, x2, x3, to xn minus 1, xn, xn plus 1, and so on. So the order must be followed because it's a chain. So that's why it's called a chain. We have a linear order of our random variables. And when we say first order Markov chain, so I'll just call this as MC. The first order Markov chain means that given the previous one, you can totally ignore what's before the previous one. So that means the distribution or the probability, I'll just write this, the probability density of xn plus 1, given the previous ones, I will write it as x1 to xn. Given all the previous random variables, is only depending on xn. So that means if I change x1 to xn minus 1, it will not affect the distribution of xn plus 1 because it's only depending on the previous xn. That's what we call first order Markov chain. Okay, so therefore you see the nature of Markov chain will let me grow the chain in a very straightforward way, right? So please note that these are random numbers. They are not fixed yet. But once I want to realize a Markov chain, how do I realize it? I need to realize them one by one. So that is, I need a distribution of x1, so I can draw a realization of x1. And given the realization of x1, I will continue a conditional on that, and then I draw the distribution. I draw x2 based on its distribution. So what actually is that? So I first draw, I'll use the lowercase realization. Draw x1, and then I will draw x2 from the distribution of, I'll just write P x2 given x1 equals the realization. I'll draw that, and then I'll draw the third random variables realization from the distribution of the random variable x3 given x2 equals the realization. Because of first order property, I don't need to care about what's x1 and continue. So that's why I can always draw next one given the previous one. That's how I'm going to do sampling from a Markov chain. So I do the sampling sequentially and to get the realization. Okay, but one nice property about the Markov chain is that under one condition, so with a condition, you can achieve an invariant distribution for those random variables. So what do we mean by invariant distribution? So that is the marginal density of a random variable xi following some density which I call pi. So what this means is that if you specify the transition probability in a certain way, then the Markov chain, each random variable in the Markov chain will be will follow a marginal density as pi. And this is actually something we called detailed balanced equation. Okay, so let's try to call that. I'm just going to quickly introduce that to conclude today's class, and we will continue next time. So by the detailed balance equation, we need to keep in mind two things. This is the invariant distribution. Okay, this is the PDF. And we also have another PDF, which is what we called the conditional or transition distribution. So this is about if I draw my xn plus 1, given my xn takes value lowercase x, this is going to be drawn from a density I call T. And in this density, there are two arguments. So one is what we have as the current state, okay, from x, and the second is the value I'm going to draw for my xn plus 1. So in other words, the x is given. This is depending on the current state, xn. So with xn takes value lowercase x, I fix one argument in my t, and the other argument is of density function. So what it means is that if I do this, so what I mean is that the txy is just equal to the probability density that xn plus 1 equals x equals y, sorry, given that xn equals x. So that's what we mean by the transition distribution. This is the density also, and it's density in terms of the second argument. So then the detailed balance equation is actually talking about the joint probability. So what it means is that the probability of, let me just say that xn equals x and xn plus 1 equals y. The density of this to happen. Okay, so I'm just going to be a little more specific. So when those two random variables are continuous, this is a joint density. But when they are both discrete, we have a probability mass function. So we're not going to distinguish those two to be rigorous here, but just know that it's either a density or a probability mass function. So this is one case. And by balance, we mean that if we swap the two values as xn equals y and xn plus 1 equals x, they are equal. So that's what we mean by balance. So it means that when the chain is in the balanced state, then we have equal probability to go from one value to the next value, and the same probability to go from the other value back to one value. So that tells me what? It tells me that my chain is not really going towards any specific value, or it doesn't have any tendency to any specific values. Because if I'm at X going to Y is equally likely as if I'm at Y and going back to X. So that's what we mean by balance. In other words, the chain is at a really equilibrium state. So when this happens, you see what it is. We are going to use the fact of probability, joint probability equals the marginal times the conditional again. So we can write this as the xn plus 1 equals y given xn equals x, okay, times the marginal density of xn equals x. This is the left-hand side. And for the right-hand side is the xn plus 1 equals x, conditioning on xn equals y, times the marginal xn equals y, right? So, and using the notation for the invariant, I have this a typo, it should be invariant distribution and the transition distribution. This is actually T x to y times pi x equals, on the right hand side is T y to x times pi y. So when our chain satisfies this, it is in the equilibrium state. And then what we can say is that all the random variables, no matter where the position is, no matter whether it's xn or xn plus 1 or any other positions, they all follow the same distribution pi, okay? So the pi is not depending on what n is. It's just the same marginal for all random variables. And the transition is just depending on what's the current xn and what's the next xn plus 1. So whenever we satisfy this, the chain is at equilibrium and each random variable follows the invariant distribution. So this is the most important property for first order Markov chain. So what's implied here is that usually in probability or in the Markov chain probability theory, what people really are interested in is that if I grow my chain following this trend, the transition distribution I specify, okay? So given the current value x, how likely is what is the distribution for the next value, xn plus 1? That's what we specify. If I keep using this transition to grow my chain, after a long while, what would be the invariant distribution for my random variables in the chain? So that's the typical question asked in probability using Markov chain. So you want to find the pi given the t. But in MCMC, we're going to use this theory in a reverse way. That is, the target density, the pi, the invariant distribution is our target, the one we want to sample from. But we are going to find the corresponding transition density to help us grow the chain. So the idea is that with our target pi, we want to find the corresponding t to satisfy the detailed balance equation. So then we will grow our chain following the t. And after we grow the chain long enough, we have our random variables in the state, in the equilibrium state. So they all follow the invariant distribution. And then what I'm going to do is to take that part of my chain, the later part of my chain, as the sample that comes from pi, and I'm done. So essentially, what I said is that in probability, the question is that given t to find pi, while in MCMC, is that we start with pi and we try to find the corresponding t to find how we should do the transition. And then we can grow the chain. And finally, we're going to take the later part of the chain as our sample that comes from pi, and we're done. Okay, so it's very interesting that although we are interested in Iid sample from pi, but we can use a dependent structure Markov chain to help us do the sampling. And this can be a very efficient way for us to do the sampling because we can keep growing the chain. And it has a very interesting property that is we don't need to really, I should say, we don't need to really like in the univariate case. What I mean is that here you need to find like an envelope density or trial density to sample from in the rejection sampling, importance sampling. But in the Markov chain, what you need is to find the transition density so you can grow your chain. So it's a very different perspective, but it has been so widely used in practice, especially its special form called a Gibbs sampler, which we'll introduce in our next and last lecture before the final presentation. So Gibbs sampler is most widely used in bioinformatics because it's a special case of growing the Markov chain, and you don't have to reject anything. You can just keep growing the chain, and then you accept the chain, the sample in your chain as your chain grows long enough. Okay, so we'll come back to that in our next lecture, and hopefully we can finish that on Thursday. And if you have any questions, please don't hesitate to ask. But I have to say that this part, because itself can be a course, right? One quarter course. So we can only cover the most basic ones, and it's only applicable if some of you want to do Bayesian modeling in the future. So you need to draw a sample from the posterior. Okay, so I'll see you on Thursday.